Hello everybody. So now let us continue our discussion on crystal engineering. So in the last lecture we were looking at solid state reactivity in organic crystals, and the field of crystal engineering was pioneered by G. Smith, who actually explored solid state reactivity in organic crystals. And it is important to note that reactions in the crystalline matrix provide extraordinary spatial control. Okay, because we already have got a very rigid matrix, and we have got the reacting double bonds which are in the vicinity of each other. So the structure provides the necessary spatial arrangement of the molecules which come into the necessary position for reacting with each other, and it also leads to a complete conversion into the final products. Unlike reactions in solutions which are diffusion controlled and involves the reactant molecules to come close to each other, and there is an activation barrier also involved in the process, in solids the crystalline matrix is very rigid. The molecules have functional groups which are already pre-organized. They are in the they are in the vicinity to react with each other, and then in the presence of a suitable stimuli, these double bonds can now react with each other to form the cyclobutane kind of derivatives. So in this regard, they provide the extraordinary spatial control. And number two, these are topochemical in nature, that is, those reactions that occur with minimum movement of the reacting species. So there is minimum movement at the atomic or the molecular level when you have a topochemical reaction. So keeping this in mind, Gerhard Schmidt first performed solid state photodimerization reactions on transenamic acid. Transenamic acid crystallizes to start with in 3 different polymorphs. That means the molecule is the same, but the arrangement of the molecules in the crystal structure is different. So there are 3 different polymorphs. We designate it as alpha, beta and gamma, and it has been observed that the alpha polymorph so we represent this by open circle. So, and they have got the arrangement of pH and CO2H is trans to each other, whereas here it is the CO2H group on the top and the pH in the bottom. And now the alpha form, it undergoes a 2+2 cycloaddition reaction to form So here you see that there is a inversion symmetry in the product, and the resulting compound is an acid. On the other hand, when you have the corresponding beta form, the arrangement of the molecules is as follows, and the beta form undergoes a 2+2 dimerization reaction to give you the beta dimer, and this has got a mirror symmetry present in the product. And in the third case, we have got the double bonds where the separation between the double bonds is greater than 4.6 angstrom in the gamma form, and therefore no reaction takes place in the gamma form, and therefore no product is obtained. So this talks about a very specific product formation happening depending upon the arrangement of the molecules in the solid state. So if you have the CO2H which are trans to each other, then we have the inversion symmetry, but if the CO2H are on the same side, then that is the cis orientation, then we have the mirror symmetry that gives rise to the beta dimer. And the prerequisite to have this solid state photodimerization reaction is that the reacting double bonds must be in the range of 3.5 to 4 angstrom, and this is within the sum of the van der Waals radii plus a bit more, but still they are positioned and pre-organized so that they can undergo the solid state dimerization to give the final product. So this kind of interesting chemistry occurs in the solid state, and now it was of relevance to see whether we can actually bring about reactive double bonds in the solid state into a position where they can dimerize with each other. So the second strategy was to make structures such that the reactive double bonds are pre-organized to undergo dimerization reactions in solid. So in this regard, what was considered is we have this particular compound, and in the presence of resorcinol, it undergoes a solid state dimerization at this particular double bond site to form the dimer. And what is done essentially is we take a stoichiometric amount of A and resorcinol B. We do the process of mechanochemical grinding where we mix the reactants in a mortar and pestle, and when we grind it for an hour and a half, and the resulting product which is obtained, or the resulting solid state phase which is obtained, is then crystallized. And after the determination of the crystal structure, it was observed that that the resorcinol has resorcinol hydrogen bonds by OH and hydrogen bond with the pyridine nitrogen on both sides. So this kind of stereochemically locks the double bond now. Now these two have come into the reacting proximity and they react with each other to form the dimer. And these are hydrogen bonded as well. So there is a you can see that there is a 2:2 ratio of the reactant materials to give you this product, and then the dimerization takes place in the solid state as well. So these points to the fact that these kind of interesting reactions can take place in solids, and this essentially provided the much necessary driving force for people to pursue more active research in the field of crystal engineering. And today there are a large number of reports on co-crystals, polymorphism, which we will discuss more in the lectures following next week. Now, the next thing which we would like to discuss is, once these hydrogen bonds have been formed in the solid state, the next thing we would like to discuss is the topology of the hydrogen bond network. The topology of the hydrogen bond network is very important, and we would like to utilize certain descriptors to describe the hydrogen bonding pattern which is obtained in the solid state, and the language that we use in this regard is referred to as the graph set analysis. The graph set analysis, that is the language to describe the way in which hydrogen bonded networks are formed in crystals. And this language can help in the identification. This helps in the identification of related families of crystal geometries, topologies, and connectivity in chemically different structures. So once you have the hydrogen bonded network, we can now identify these hydrogen bonded networks in related families of different crystal geometries, topologies, and connectivity in different structures. So we would like to now discuss this graph set analysis, which was actually developed by Margaret C. Etter in University of Minnesota, followed by Joel Bernstein and Raymond Davis. So to start with, all hydrogen bonded crystal structures can be reduced to combinations of 4 simple designated patterns. 4 simple designated patterns. Number 1 is chains, which we represent as C. Number 2 is rings, which we represent as R. Number 3 is an intramolecular hydrogen bond, which we represent by S, which represents as self. And number 4, discrete D for other finite patterns. And to these fundamental descriptors is added a subscript denoting the number of hydrogen bond donors in the pattern, symbolically represented as D, and a superscript denoting the number of acceptors, which is denoted as A. The total number of atoms including hydrogen in the pattern is termed as the degree of the pattern and symbolically written as N, and this is also given in brackets after the pattern descriptor. So the total graph set descriptor is symbolically written as G A D N. So these are the fundamental rules on which the graph set analysis has been constituted. The structure containing only one type of hydrogen bond is called a motif, and can have one or more graph set descriptors associated with it. And when you have more complex crystal structures where more than one motif is present in the structure, then you have to assign graph set descriptor for every motif separately. So the graph set descriptors have to be assigned independently, that is individually, for each motif as if the others were not present. And this is called first level graph set and written as N1. So now let us look at these different graph set descriptors with suitable examples. For example, if we are to first look at the chain which is being formed, we already discussed the formation of a chain. For example, we have a benzamide molecule. So it forms a chain, and between one molecule and other, the number of atoms which separates a chain. So between this hydrogen bond and this hydrogen bond, the number of atoms which separate the chain is the longest possible chain which contains the maximum number of atoms. In this case, it is 4. So this is referred to as a C4 graph set descriptor, C representing the chain and 4 representing the number of atoms which are repeated in the pattern. So when the pattern is being formed, this is the number of atoms in the pattern which is repeating itself, that is C4. The next one is to look at a dimer, and in this regard we can look at the classical carboxylic acid dimer. And this is represented by the graph set descriptor R. A represents the number of acceptor atoms, so there are 2 acceptor atoms. D represents the number of donor atoms, there are 2 donor atoms, and the number of atoms in the motif or the graph set descriptor is 1, 2, 3, 4, 5, 6, 7, 8. So R2 to 8. So the cyclic motif, the dimeric centrosymmetric motif, is represented by R2 to 8. We can consider the case of intramolecular hydrogen bond. For example, we can take orthohydroxybenzoic acid, where we have this intramolecular hydrogen bond present, and the total number, so it's a self cyclic motif, it's an intramolecular hydrogen bonded system, and the number of atoms present in this descriptor are 1, 2, 3, 4, 5, 6. And normally when the number of donors and acceptors is equal to 1, then that is not mentioned. So when there is only one type of hydrogen bond and there is only one donor and one acceptor, you don't have to mention the number 1, you can omit that. And D, that is a case of a discrete motif. We can now take a case where we have triphenyl phosphine oxide hydrogen bonded with hydrogen bonded with phenol via OHO hydrogen bond, and this forms a discrete motif represented as D, and the number of atoms in a discrete motif is 1, 2, 3 and 4. So the graph set descriptor for such kind of motif is D4. So in actual crystal structure, you can actually have more than one type of motif, and then as mentioned, you will have to consider every motif utilizing a different graph set descriptor, and the combination, the product of all these descriptors will represent the first level graph set, for you. And in this regard, Etter's rules have been proposed. Etter's rules have been proposed, which are used for predicting and forecasting solid state arrangements. And what does the Etter rule says? Number 1, all good proton donors and acceptors are used in hydrogen bonding. And number 2, 6-membered intramolecular hydrogen bonds are formed in preference to intermolecular ones. So these two are the fundamental rules on which the fundamental rules on which solid state arrangements can be predicted. Obviously these are just a set of rules. They can be applied, and sometimes they work, but it is not necessary that the Etter's rules will work in all the cases. However, in cases where you have got strong donor acceptor groups like acid, amide, ureas, anilines, imides, and phenols, the first rule works very well, and the justification for the second rule is similar to that of the Chelet effect. That just like the Chelet effect stabilizes the ring-like structure, in this case also the cyclic structure wherein a proton is essentially chelated between the two donor atoms is what provides the extra stability to this hydrogen bond, and hence it is preferred in comparison to the intermolecular hydrogen bonds. And let us take up some more examples of applications of graph set analysis. For example, we can consider NH interacting with, we looked at this motif. So this is a ring motif which has got acceptor is 2, the number of donors is 1, there are 2 acceptors and there is 1 donor, and the number of atoms in the ring is 1, 2, 3 and 4. So when you have an NHO hydrogen bond involving the nitro group, then this kind of a motif is formed, and this is also a representation of a 3-center hydrogen bond. We can have amino functionality which can interact with the nitro group, and here it will be R22, 1, 2, 3, 4, 5, 6. So this is the graph set descriptor, and this is a case of a hydrogen bond and NHO hydrogen bond. So similarly we can look at diaryl ureas. So in this case we have 2 sets of hydrogen bonds, and we can first describe the cyclic one, that is the R1, which has got 1 acceptor, 2 donors, 1, 2, 3, 4, 5, 6. So this is one the acceptor is 1 and the donors are 2, yes, and we have got another one such that the chain repeats itself, that is this particular C4 unit. So this is also present. So both these graph set descriptors are present in diaryl ureas. Okay, so this is interesting in the sense that we have got now 2 donors and 1 acceptor. We can also look at other types of motifs. For example, we can look at NH, we looked at the structure. So here we have got 1, 2, 3, 4, 5. So we can have this NHO 1, 2, 3, then 4, 5, 6, 7, 8. This is one 8-membered ring, and then we can also have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we can have R2 to 12, and we can have R1, 1, 8. So this is the first one is the primary graph set analysis, that is this one. Okay, here we have got 1, 2, 3, 4, 5, 6, 7, 8. We have one donor and one acceptor. Whereas in the we can also consider another graph set analysis where we have got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and there are two donors and there are two acceptors. This is the secondary graph set analysis. So instead of talking about two independent primary sets, we can talk about one independent primary set and a much larger graph set descriptor, which essentially covers the larger size motifs, which is represented as R2 to 12. So in this way, graph set analysis is very useful to understand the arrangements of different hydrogen bonds in different crystal structures, and particularly in case of polymorphs, this is very useful to differentiate between the different hydrogen bonding arrangements which govern formation of polymorphs. So with this, we have come to an end of this particular week's lectures, and in the next week we will go to the other set of topics related to polymorphism, co-crystallization, and explore other relevant phenomena in the solid state. Thank you.